Welcome back to AlgoJS. Today's question is LeetCode 39, combination sum. So given an array of distinct integer candidates and a target integer target, return a list of all unique combinations of candidates where the chosen number sum to target. You may return the combination in any order. So the same number may be chosen from candidates an unlimited number of times. Two combinations are unique if the frequency of at least one of the chosen numbers is different. So it is guaranteed that the number of unique combinations that sum up to target is less than 150 combinations for the given input. So here in the example, we have candidates 2, 3, 6, 7 and a target which is equal to 7. And in the output, we have 2, 2, 3 and 7. These are the only two options of candidates that are going to add up to 7 within this candidate list. So the key thing to take into consideration here is that with the candidates, we can take an unlimited number of any of these candidates. So we need to make sure that we aren't going to be taking duplicates. So with this question, we can utilize a recursive solution or a dynamic programming solution, which could either be done iteratively via a bottom up or recursively via top down. And today we're going to utilize the recursive solution. So let's look into that. So with our recursive solution, we are going to have base cases. We need to work out what these base cases are. And the best way to do that is run through what this tree is going to look like. So at the top, we're going to have the target, which is 7, and we're just going to subtract at each stage a candidate from this target. So at each stage, we have 4 potential options initially. So let's say we follow 2. Remember, we are going to be returning an output containing the candidate, so we need to have an array which is going to be storing every candidate we take at each recursive call. So we're going to have an array here which is going to contain the candidate which we've taken. 7 goes to 5. At 5, we have another 4 potential options. So we have 2, 3, 6, and 7. Let's just stick with 2 for now. So we take another 2. We add that into our array of candidates taken. This goes to 3. We take 2 again. This goes to 2, 2, and 2. Oops. We're at 1. We take 2 again. So 2, 2, 2, and 2. This is now less than 0. So this is not a valid option. So we have reached the base. So we can say if target is less than 0, we can return. And when we return, we need to backtrack. So we need to pop the last value off this array to go back up. And at 1, we can also take 3, 6, and 7. So 3, 6, and 7. Now these are all going to be less than 0, so I'm not even going to look into those. But we need to backtrack at this point. So pop off the stack at the last value. Go up to the previous call in this call stack. At 3, we have 3 other options. We can take 3, 6, and 7. So if we take 3, it's going to equal 0. So we have 2, 2, and 3. And this is a potential solution. So this is another base case. So if target is equal to 0, we're going to have some auxiliary data structure which is going to store our results. Let's call it res. We're going to push into res a copy of the array of candidates that we've chosen, that we've accumulated as we go down this recursive call. So it's this array right here. And the reason we're making a copy is because we are going to be manipulating this further. So say at this point now we've reached the 0, we're going to pop off of this, we're going to go back up to 3, we're going to check 6 and 7. So we're going to be manipulating, we're going to be mutating this array. So we need to create that copy, and this is going to be ON time complexity. Okay, great. So we found this answer right here. So we're going to pop off the stack, we're going to search for all other potential solutions within this side of the tree where we've taken 2 initially from 7. And we're going to realize that all values are going to be less than 0. So there's no potential solution down this side. So let's say we take 3 now. So we take 3 from the top. 7 minus 3 goes to 4. And let's say we have 4 potential ways to go from here. So we take 2, 3, 6, and 7. Now if we take 2, we have 3 and 2. This is going to go to 2. Let's say we take 2 again. So we have 3, 2, and 2, where we've taken 2. This goes to 0. We found an answer. But as you can see, this array right here is equal to this array over here, which I will actually populate this answer within results. So we have 2, 2, and 3. This is the exact same as this. So we know that we can't go down this way because we have duplicates. And the way we resolve this is, rather than at this stage, we take 2, 3, 6, and 7, we take everything from 3 onwards. So we exclude 2 now. 2 has been seen. We've gone down this recursive call down here where we've taken 2. We don't need to take it any further. So now when we take 3, we are only going to take 3, 6, and 7 as potential options in this recursive call. And if we branch out into all of these, we are going to have less than 0, less than 0, less than 0 in all of these subtrees. So there are no potential solutions in that one. So all the values that we take when we take 3 initially are going to be less than 0. So let's move on to 6. So we take 6. Remember, in this recursive call, we aren't looking at 3 anymore. So at this position, 3 has already been seen in this recursive call down here, so we can exclude that from the search. So if we take 6 here, 7 here, so that'll be 6 and 6. This is going to be less than 0. And this is 6 and 7. This is going to be less than 0 as well. So neither of these are valid options. So we have now seen 6. And last but not least, we need to go and take 7. So let's say we take 7. We reach 0. That is an answer. So we can add, or we can push that into results as a copy. We've seen that. We move along. So we pop off the stack here. We're back at 7. We move along the candidates. We have no more. So we can return this as the result. So time complexity for the solution, we're going to have an upper bound. So it's going to be ON, where N is the number of candidates. We have to times this by T over M, where T is the target value that we're looking at, and M is the minimum value within candidates, plus 1. And this T over M plus 1 is the maximum depth of this tree. And then space complexity is going to be O T over M. Okay, so let's create the result array and our DFS function. So with DFS, we're going to pass in 0, target, and an empty array. So 0 is going to be the index, and I'll show what that's used for in a sec. Current val, and then we are going to call the last array. Right, and this is going to be the array that we're going to populate with the candidates that we have taken at each step. So we need to set the base cases. So if current val is less than 0, we can return. So we haven't found a potential solution. If current val is equal to 0, we can push into result a copy of the array that we have created. And then we need to loop through, so let I equal index, I is less than candidates, dot length, I plus plus. So at this stage, we're looping through index, which is equal to I. So each stage, we're adding 1 on to I. That means that we can avoid duplicates, and then we need to push into our candidates at I. Then we need to carry out the recursive call. So DFS, remember to pass in index, which is now updated to I. The current value is going to be current value minus candidates at I. So we need to subtract that value from the target. And then we need to pass in the array. And finally, we need to make sure that we backtrack. So we need to pop off of R. And then we can return result. Okay, let's submit it. And there you go.